Hello, and welcome to the Fall 2020 ELECOMP Virtual Symposium. We are Team TACO BLE T-Stat, and our project is to develop a 2-wire Bluetooth low-energy thermostat adapter. Our technical directors are Evan Cornell, an embedded controls engineer, and Jack Kang, an embedded software engineer. Our team is made up of one computer engineer, Johann Carl Mueller, and two electrical engineers, Tyler Aceto and myself, Eric Burlow. TACO Comfort Solutions is a third-generation, family-owned company based in Capstone, Rhode Island, with manufacturing facilities throughout the states and globally. They engineer high-efficiency heating, cooling, plumbing, and water irrigation systems, and manufacture products such as water circulators, precision pumps, zone valves, and hydronic heating controls. The focus of our project is in hydronic heating system control. Most households have mechanical thermostats which operate just like a switch. When the room is below a set temperature, the switch closes and the heating unit turns on. Recently, smart thermostats have gained in popularity. They have user-friendly settings and are more energy efficient, leading to their increased demand in the marketplace. These thermostats, however, require a third constant 24-volt wire for ideal operation. This means that it's necessary to run new wire from the thermostat to the heating unit, which is usually located in the basement, making it difficult for the homeowner to upgrade. The motivation for this project is to allow for easy installation of smart thermostats in hydronic heating systems using existing 2-wire thermostat cables. Our anticipated best outcome for the project is to develop the hardware and firmware needed to pass power from the control unit to a smart thermostat through the two existing thermostat wires, and also transmit a Bluetooth low-energy signal from a microcontroller to the control unit when the thermostat heat call changes. Our key technical accomplishments include component selection, hardware design, and firmware development. The primary components needed are the microcontroller for BLE communication, the voltage regulator for powering the microcontroller, and the optocoupler for isolating the heat call signal. The hardware design requires simulating and testing these two circuits, drafting a PCB layout within our size specifications, and building and verifying both of these prototypes. For Bluetooth communication, the goal is to design a hardware abstraction layer to develop firmware that is both reusable and hardware independent. With an increased demand for smart thermostats, there is a need for retrofit installation designs. With the completion of this device, homeowners are more likely to upgrade to a smart thermostat, increasing sales of electronic controls, and therefore increasing TACO's position in the hydronic electronic controls marketplace. Here is a block diagram of the overall design. The device we're creating is represented by these blue objects. As one of the electrical engineers on the project, I am focusing on the hardware design, primarily the power management for the device. For power management, the goal is bringing power to the microcontroller. For this prototype, we used a resistor to represent the average current that the microcontroller would draw during BLE communication. The first task is to convert from AC to DC using a full-bridge rectifier shown by these 4 diodes. After the rectifier, a voltage regulator is needed to step down to 3.3 volts. We decided on a linear dropout regulator, or LDO, since it is more cost and size efficient than a buck converter. The LDO works as a feedback circuit that monitors the input and linearly adjusts the output as the input voltage changes. The input and output capacitors have a great deal of effect on the stability of the output voltage, so a lot of simulations were needed to decide on 10 microfarads for the input and 2.2 microfarads for the output. Here are the oscilloscope shots showing the performance of our voltage regulator. On the left is the DC coupled output showing 3.3 to 3.4 volts, which is the expected output voltage. The blue wave on the right is the DC rectified input, and the yellow wave is the AC coupled output ripple, which is about 18 millivolts. This electrical noise is caused by the oscilloscope ground probe and can be reduced by shortening the ground connection. It's also worth noting that the current draw in the system is being replicated by a resistor, and so it's not an exact representation of how the microcontroller will act during BLE communication. The other hardware design aspect is the isolated heat call circuit. For this, my colleague Tyler Aceto will go into more detail.
Thank you, Eric. As Eric mentioned earlier, a traditional thermostat acts as a kind of temperature-sensing switch. When the temperature in the room gets too low, the switch closes, allowing the 34 VAC heat call to travel to the control box to activate the heating unit. However, in our case, the heat call is traveling to the microcontroller, which can only handle about 3 volts. So, we needed to somehow isolate the microcontroller from the 34 VAC in order to avoid damage. In order to achieve this, we used a device called an optoisolator. The working principle of an optoisolator is pretty simple. Power is supplied to the infrared LED, causing it to emit light, which is then picked up by the phototransistor, which opens, allowing current to flow through. In this way, we are able to transfer large electrical signals contactlessly without the risk of damaging the receiving device. For our project, we chose the FOD817BSD based on its price and performance. Here we have our heat call circuit. On the input, shown in purple, we have a current-limiting resistor and a rectifying diode, since the optoisolator is monodirectional and reverse voltages would damage the LED inside. In green, we have the optoisolator. When the heat call is sent through the LED, the phototransistor activates, allowing current to flow from the 3.3 volt LDO output, shown in orange, through the current-limiting resistor, shown in pink, into the pin of the NRF52805 microcontroller, which is shown in red. The microcontroller then sends a heat call to the takeout control box on the heating unit via a Bluetooth antenna. Here we have our PCB layout. In orange, we have our screw terminals, where we slot the wires that connect our board to the existing system. In green, we have the power management circuit with the AC-DC rectifier and LDO. In yellow, we have the heat call circuit with the optoisolator, the rectifying diode, and the 2 current-limiting resistors. In red, we have our microcontroller and its reference circuitry. In blue, we have a routed Bluetooth antenna. And in purple, we have the debugging connector for the microcontroller, which is mounted on the back of the board. That concludes the hardware design. My colleague, Johann Karl Müller, will now go into more detail about the microcontroller and firmware aspects of the project.
Thank you, Tyler. For this project, we had the job to choose a microcontroller capable of BLE connection, compatible with TECO's libraries, and in accordance with our budget limitation. Since TECO's other point of communication is using a NORDIC controller, it would be easier to make it compatible if we choose a NORDIC controller as well. After making a list with all NORDIC controllers capable of BLE connection, we compared specifications and price. NRF52805 was the cheapest and more compatible match. It has Bluetooth 5.2 supporting BLE, 64 MHz M4 ARM Cortex with 192 kilobytes of flash and 24 kilobytes of RAM. NORDIC has a set of libraries called Soft Device that deals with Bluetooth Low Energy Stack, making it easier to configure and connect the application layer with the physical layer. We are going to make use of this library alongside with TECO's library to program and configure Bluetooth Low Energy connection. Our initial thought about how BLE will be organized is having 2 services and each service having 2 characteristics. One of the services will be to identify the company and firmware version and allow the possibility to update the firmware. And the second service will be related to the heat signal and additional information that we need to pass through connection. Here we can see a general flowchart of how the program will work. We have 2 threads, the main thread in the left where we keep connection to TECO's central unit, and on the right we have a pseudo thread generated by a timer interrupt that will be reading the heat signal and updating that information on the main thread. Our future accomplishments include fabricating the PCB, continuing to develop and debug the firmware, and field testing of the final prototype. We would like to give special thanks to our 3 technical directors, Evan Cornell, Jack King, and Robert Kelliker, for always being available to answer our questions. And of course, thanks to our consulting technical director, Mike Smith, and our project coordinator, Dr. Sunak, for everything they do for the Capstone program.